Hi everyone and welcome. Thank you for joining. It's Simon speaking. This is the first session I'm doing, so I will do my best. The topic today is reinforcement learning. It's a quite large topic to cover, especially in 1 hour. So what I will do, I will take two goals. The first goal for me is to give you the definitions and the concept, especially about what is not RL, so that you can navigate in the large number of news covering this topic and give you the reading grid. The second objective I have is to show you that actually reinforcement learning holds quite a lot of intuition about human behavior. So I will do some parallels and to show you that RL concepts can actually be transferred to your everyday life scenarios. That's the goals. Probably not so much cover in the other YouTube video, so I hope you will enjoy it. Before I forget, all the sources and references of the pictures I'm using can be found in the description. In this presentation, I will be mentioning some research trends about decision making and reinforcement learning applied to autonomous driving. And I have recently published an informal paper on these topics, so feel free to have a look. It is available on ResearchGate and on my GitHub as well. It comes with a very long list of references, more than 90 total, so just have a look if you are interested in these topics. And finally, let just me mention that you can find the code of the example I'm using in this presentation. It's also available on my GitHub, and it comes with the implementation not only of model-free algorithms, such as Monte Carlo control, Q-learning, expected SARSA, and SARSA lambda, but also for model-based planning with dynamic programming, policy evaluation, policy iteration, value iteration. And in addition, you will find the definition of a simple world environment to test the algorithms. Simple but convenient for educational purposes, and once again, have a look at the description for more details. And I really want this session to be interactive, or at least dynamic, so there will be some times for quiz. So stay attentive. As soon as you see this symbol, you know that there will be a question coming. All right, first question. Who are these two mathematicians? So the first one comes from the USA, is Richard Bellman. If you don't remember about the second one, it's probably because of the memoryless property he has developed. He is the Russian mathematician Andrei Markov. They will be joining us today, and they are responsible for all the equations we will be seeing. So we will need some math to set the problem with the Markov decision process, and then we will use the Bellman equation in the framework of reinforcement learning to solve this problem. At the end, I really want to keep some time speaking about the perspectives of reinforcement learning, especially in autonomous driving. But before that, let's start with concrete examples and applications to give some definition and have some intuitions about reinforcement learning. Let's start with machine learning. You probably have heard of it. This is the science of getting computer act without being explicitly programmed. In other words, this algorithm have performance that improve over time as they are exposed to more and more data. And it can be divided into three classes. This is a simplification, but three classes, let's say: supervised learning, unsupervised learning, and reinforcement learning. You may ask, okay, now the question is, how to distinguish? I'm giving you a method. Which of the three is applied? Well, I find it convenient to ask two questions. The first one is about the dataset you are using when training. So training is when you are developing a model, improving your model, but it is not testing. This is not in production. This is still in development. So the dataset, where does the data you are using come from? Is it from a static dataset? In this case, the first two can apply. Or is it from an environment? The environment means you are interacting with it. You are the agent and you are interacting with it over steps. This is the first difference you can have. The second one, in all the three cases, you will be giving answers. And the question is, then this answer, how is it evaluated? How is it assessed? For the fixed data set, you can have a ground truth. It can be called a target. It can be called a label. You have something to compare with. This is not the case with unsupervised learning. And finally, this is totally different with reinforcement learning, since, as I said, you are doing steps, and for each step, you receive a little reward. And what is important to you is, of course, these rewards, but more important is the sum of rewards. And that tells you if you act correctly or not. Let's take some examples. So here we have an images. The task will be to draw some bounding box around the objects and to say to which class it belongs to. And then this is compared to some, let's say, ground truth. Someone or something has spent days or even more time defining what is expected as an answer. This is supervised learning. There has been a supervisor. Here we have Alex and Bob. So Alex and Bob have the same hobbies, the same alimentation, and yeah, Bob has bought some soda. So why not recommending or making an offer? This is the concept of clustering, recommendation of unsupervised learning. Now for reinforcement learning, this is an example where you have to try and to learn to turn this valve. At the beginning, you have no idea how to do. So you might be stuck without doing anything for a couple of minutes or even more. Here you see after 4 hours of training, he's able to turn it. And yeah, you are interacting with the environment, trying things. Maybe the reward can be the angles. Is it going in the direction I want it to go, i.e. I am turning the valve in the good direction or not? So there are 3 conclusions now. The first one is, for reinforcement learning, you need an environment. The second one is it's a multi-step process. Here you can see you can divide into time steps. And the last one is we have 3 subclasses for machine learning. They are not competitors. They are just serving different purposes. So the 3 are not in the same league. Nevertheless, one could compare their popularity. So with the Google Research Index, we can compare unsupervised, supervised, and reinforcement learning. Reinforcement learning appears here in yellow. You just see that it's quite recent and it's booming. In the International Conference on Machine Learning in Stockholm this year, the biggest room was for RL, and most of the papers were covering this topic. So a huge interest for researchers. For applications, the applications are limited for the moment mainly on video games, robotic control, and a little bit of autonomous driving. Let's see some examples about reinforcement learning for video games. That's the opportunity to introduce new concepts. We have seen so far the concept of environment, the concept of step. Now let's see what a reward is, what an action is, and what a state is. With the game of Go, so what you have here is a board, and the board actually, with the position of the stones, give you all the information you need to know in order to take action. So what you want to do is take the position in the grid and code it in an array, for instance, and that will constitute your state. Think of the state as the configuration or the description of the current situation. And then comes the action. So one action could be, I want to put one stone at the whatever position, and that would be an action. And then this is one step. Then you wait for the other to play, then you have to do another step. And for each step, you are getting a reward. It might be null. That's a choice on the designer. So what I can do is I put 0 as a reward for each step apart from the last one. And if you lose, the final step you are doing will bring you -1 and +1 in the case of a win. That's the main idea about action, state, and reward. This is another example taken from the Udacity course about reinforcement learning. So what I was doing, my task was to collect bananas. You see the action is turning left, turning right. What is the state? One possibility would be to have the state as one screenshot. So each image is one state. And the reward, it might be null if for each step I do without collecting any banana. It might be +1 if the banana I collect for this step is yellow, and it might be -1 for the banana which I collect is blue. And you have the feeling now, okay, one step reward is important, but what is more important is to collect over time. So the sum of the rewards I'm getting, this is what you want to maximize. Okay, this is simple games. Now, serious business. So last month, there has been OpenAI, so a research group for reinforcement learning, defeating a former, some people really talented at Dota 2. So Dota 2 is a game where you are in a team of 5 and you are fighting against another team of 5. The difficulties here comes from 3 things. The first one is you don't have a full knowledge of the state, i.e. you don't know everything about the environment you are in. For instance, because of fog or cloud, you don't have a full access at the description, or the position or the position of the opponent is unknown for you. That's the first difficulty. Second one, you are playing in a team against a team. So it is actually collaborative. You have to think of your teammates, and adversarial, so collaborative and adversarial. And this is not so obvious to solve. And the last one is that compared to Go, this is a continuous time process. i.e. for Go, I'm playing, you are playing. I'm playing, you wait, and then it's your turn, and so on. Here, at the same time I'm moving, the other people are moving as well. So that makes it really difficult. So that there are a couple of examples for video games. Atari is another one. That now you can ask, okay, Google, why are you investing so much money in solving video games? And actually, this knowledge of reinforcement learning can be transferred to other domains such as robotics and control, where there are much more money to earn. This brings us to the applications of RL in the domain of robotics and control. Robotics, remember this example of the valve, the robot has to turn. And for control, this is a recent achievement covered by, reported by Google about controlling the cooling system in a data center. The point of this slide is to show you that reinforcement learning is really close to the control theory. It's not about perception. It's not about sensing. It's really about decision making and decision implementation. All the decisions you are taking, turning left, turning right, this is an ID, a decision, intuition, they will be implemented as part of your interaction with the environment. So have in mind, reinforcement learning is really about control theory, or close to control theory, and about decision implementation, as opposed to the perception field of or area. This is important to have in mind, in particular when you try to apply RL to the domain of autonomous driving. And taking the classical modular pipeline of autonomous driving. So you start with perception. Your task is to identify where you are, your current speed. So all about sensing where are the others, where I am on the map, localization and perception. Then comes the task of decision making, when you are deciding, okay, I want to turn left or continue at this speed. And then this decision is actually implemented with a controller having the control of the wheels for the steering angles, or the gas pedal for acceleration. One could draw a parallel with the human when we are using our eyes, then brain, and then muscles to see, decide, and act. With what I've just been saying, reinforcement learning can apply to only the line 2, i.e. when you are making decisions, and then they will be implemented. As opposed to perception, where supervised learning is often used, this is a different problem. So now there are 3 research. One could classify reinforcement learning for autonomous driving into 3 research trends. The first one is about intersection handling. So imagine you have different kinds of intersection to address. It might be complex, and the task, what is asked, is to have something generic that can solve all possible configurations of intersection. The second one can also use as an environment a simulator. This is a highway scenario. We will cover it in the next part. And the last one is end-to-end reinforcement learning. We will mention it in the coming quiz. Time for it. Let's take this example. So I'm giving you this picture. Consider that it is a state, and the action you have to decide to take is how much should you turn the steering angle of the car in order to stay on the road. That's the problem. in a simplification of what NVIDIA was reporting, what they have done is they have asked a human to play the environment, and then they have recorded for each time step both the image and the decision applied, or let's say the steering angle applied by the human. So doing, you can constitute a big data set, and then back to the office, you can learn a model that matches for each image, gives you a value of steering angle. What I want to show you is that, okay, this works, we will see a video, this is impressive, but this approach is not reinforcement learning at all. Although I have been using terms like environment, steps, action, state, and so on, this is purely supervised learning. You have been using an environment, but not for training, only for recording data. And then you have been applying classical regression methods. So yeah, be careful. I'm not so fan of this terminology because you don't know which of the three methods of machine learning applies. Be careful when reading it. And the video is quite impressive. And the power of generalization it makes. This is, riding everywhere. Let's go a little bit further. Also, in the night, you are able to drive. Yeah, quite impressive. So a couple of examples. Now, time to sum up. What we have seen is, this is informal, but we need an agent. An agent, and we need an environment. This is not a static database. The agent is playing, interacting at each step with the environment. A step is the single motion where you have to take an action to transition from one state to another. What is called an episode is a list of steps which ends at the end, or at the termination step. So concretely, when playing Go, the episode is from the start until the end when someone wins or loses. This is an episode. For each step, we have seen that, for instance, for the bananas, we get rewards, -1, 0, or +1. And what is important is we are trying to maximize the sum of them. We collect them and we try to maximize the sum of it. We have seen that reinforcement learning is quite close to control theory in the way that your decisions, turning left, turning right, will be or are implemented directly in the environment. And finally, with the valve example, we have seen that it's really about trial and error. So you start having no idea, you might be stuck with this valve, not turning it for a couple of minutes, but then trying to get it better and better. And we improve with experience. That's the informal definition. Now, so a more formal definition, reinforcement learning is an area of machine learning concerned with how software agents should take actions in an environment so as to maximize some notion of cumulative reward. This is exactly what we have been saying in the intuition. Maybe just cumulative reward. Again, what is important is not the one-step reward you will get. What is important is to think over a time horizon. This horizon may be short, may be long, but this is the cumulative sum, the sum of the rewards that is important. Well, how do we start then? In machine learning, the environment is typically formulated as a Markov decision process. So the modeling part is with MDP. You will find most of the problems are already formulated, defined. This is the case, for instance, if you are playing with OpenAI GIM environments. So the task is then to solve the problem, but the modeling part is already done. Nevertheless, I find it really interesting. This is the reason why I'm mentioning it. And we will see how it works. But for the moment, distinguish the problem setting, Markov decision process, from problem solving using the reinforcement learning framework. And to help us, this is the big picture to keep in mind. You have the agent playing with the environment. The agent starts, is saying, I'm in the state S, I want to take action A. The environment takes these two information and transition, so move the agent to a new state S prime and give our agent a reward A. So let's consider a very simple case, for instance, where the state is your driving velocity in a city. Yeah. So only one information in the state. you are at speed 50, this is S, and you want to speed up, this is A. The agent, in this case the car, will take you at speed let's say 60, so more than 50, so you have speeded up. Comes with that the reward, which is negative in this case because this is bad to drive too fast in the city, and that's basically constituting one step. What does the agent can do from this one step? He collects the 4 information, so S, A, S prime, and R, and this constitutes a tuple of 4 elements, and you can store this tuple in the memory of the agent. And for the next time, the agent will use this experience to adapt or improve his model, and won't probably speed up while being at 50 kilometers. This is, to me, exactly or really similar, really close to how human use experience to adapt the action for the next scenario. So before we move to MDPs, a quick quiz about the environment. I will be comparing, or we will be comparing, the game of Go and another environment of, let's say, autonomous driving, for instance, urban environment, where you have to decide which maneuver to take. There will be a list of criteria, and for each criteria there will be a simple and a difficult version. And the question is, which of the two applies to both Go and autonomous driving environment? The first one is about the state. We have said the configuration, all you need to know, or all you could know about the situation. And the question is, can you have access to the full state, or is it only a part of it? So for Go, remember, we have this grid, and both players actually see the full grid. So it's a fully observable case. On the other hand, for autonomous driving, you have no idea if there is a car in front of the truck you are following, or if there is someone coming from left at the next corner, if there is a building in between. So that's the first distinction, observable or partially observable. Now about stochasticity in transition, what does that mean? Remember, we make decisions, and we give this decision to the environment, and then the environment move us to the next state. The question is, when moving us, is there any randomness or stochasticity? For Go, there is no, because when I think, okay, I want to move, or I want to put this stone at this place, this is 100% sure, because I'm in control of it, that this stone will end up at this place. On the other hand, for autonomous driving, let's say your decision is, okay, I want to stay in the middle of the lane, but for some reason you are close to the sea or whatever, and there is a strong wind coming from the left. Suddenly, you couldn't predict it, and then it moves you. But then the next state, you are not in the center of the road, not anymore. Although you thought, okay, I'm doing the right action to keep this state. So stochasticity in the transition versus deterministic transition. How many agents? That's quite obvious. It can be adversarial or collaborative. It is adversarial for Go. It can be both for autonomous driving. Okay, multiple agent. The question for autonomous driving is, do you want to collaborate with the other participants? It's possible with communication protocols, and this is what is called V2V, vehicle to vehicle, for instance. The time evolution, with Go, I am playing, then I stop, then you are playing. Then you stop, then I'm playing again, and so on. So this is sequential. This is continuous. All agents are moving at the same time for autonomous driving. State space, it can be, of course, discretized in the case of autonomous driving, but it is originally continuous. In a sense, my velocity is something continuous. It's encoded with a float. On the opposite, the Go, you have a grid, so you can code it with integers. It's totally discrete. And the same applies to the action space. Discrete for Go, continuous for autonomous driving. What I want to show with this slide is that autonomous driving contains all of the difficult parts. There are simplifications to make, of course, but it is at itself, from scratch, a very difficult problem. What does make the difficulty from Go. It's about the state. The state is really huge, and it's about the delay reward. You are playing on average 120 steps in one episode, and you only get one reward at the end of the 120 steps. So that's the difficulty. That was about the environment. Now let's have a look deeper in what the MDP is. So MDP, Markov Decision Process, we will start easy, ignoring the decision. So only Markov process. There will be a quiz. We will be using this example of Monopoly, so we'll take an easy version of it. The point is to illustrate, again, three concepts. The first one is the transition function. The second one is the state. We have already mentioned it. And the last one is about the Markov property, of course. So we just said we ignore the decision part. So we don't need any agent anymore. There is no action being taken. There is no reward being get. We are just spectator, in a sense, of a transition from state S to state S prime. And we are playing with this board. So if you remember the previous classification, you can say that is a fully observable environment. It's also discrete in terms of state. There is no action, and the most important part is transitions are stochastic. Stochasticity means they are randomness induced by rolling the dice. So now, having said that, let's define the rule. You have two dice. You roll them, and then you move according to the sum of it. So if you are, you move 8 forward in this case. You do that all the time except in for one condition, and this condition is based on double. So here you see 4 plus 4, you have made one double. If you do a second double just after, then it's a double, and then you go to jail. This is one rule. Let's go with it. The question is, how do we encode the state? Encoding the state means, or designing the state means, which information do we need, or how do we describe the configuration or the current situation? Obviously, we need the position. So there are 40 positions in this board. We'll need also the information about, in the previous step, did we get a double? Yes or no? And then in the previous step, did we get a double? Yes or no? Okay, that's our state. Now we just leave the process run, and then we observe it. And one question could be, okay, how much time is spent on average in jail? This is a question I am leaving to you. All right, now let's take the opportunity to mention two concepts, the transition function and the Markov property. What we have said is that in our state, we have the position. How many positions do we have? 40. We have also a Boolean, i.e. yes or no, about the previous double. So two possibilities, and another two possibilities for the previous double. At the end of the day, we have 160 states. So you can think of our current state to be one of these. And then one question we could ask is, these are the candidates for the S+1 in the next step. So where do we go? Where do we step in? And the answer is given by probabilities. And this is, for instance, the probability to go from state 1 to state 2. And you can fill this table, transition function table. What you see is that in order to predict the state st+1, the next state, you just need the st. Nothing else is needed. st-1 is not required to do this term computation. This is because the state was designed, let's say, correctly, or at least it holds the Markov property. And the Markov property says st+1, the state at time t+1, only depends on st, the state at time t. In other words, given the present, the future doesn't depend on the past. And this is a strong assumption for most problems, but really useful. In particular, you can think of what happens for the memory. If we don't have this property, and if we have to store or to consider, I don't know, the last 100 state, to predict the next one. It really quickly becomes intractable. Here we have already 160 states. You can think of problems where there are way more, and doing the combinations, it becomes exponentially or really quickly intractable. That's a strong assumption, but useful and proper to this Markov decision process. So remember the question, how much time spent on average in jail? Now that we have this table, these transition function probabilities, it can be used to solve this question analytically. Otherwise, what you can do is go for Monte Carlo methods. And it has been done here. Again, the source and reference is available in the description of the video. So with this example, we have seen a Markov process where there is no decision. We saw the transition function, the initial state, and the state space we designed. Now it's time to introduce actions. So actions and reward. So we see now with agent back, we can make decision, we can change the world, so to say. And we will introduce reward function, action space, and two parameters, the horizon and discount rate. So let's see the definition of a Markov decision process. We have said it's about modeling a decision-making problem. And we have two components, stochasticity and control. Stochasticity, this is the monopoly example, where the outcomes comes from randomness. We have no influence, no impact, we are spectators. But in Markov decision process now, it's partly under our control. There will be some wind on the road, so we won't control everything, but at least turning left and turning right won't have the same impact. The Markov property has to be included in it, in Markov decision process. Again, next state is only a function of the previous state, and this time action and the previous action. Of course, there is stochasticity in it, but there is no part reserved for past. You can ignore the past if you have the current state. It holds all the information you need to have. Now introduce what's called the policy. We have mentioned state and action. When you are playing, you might ask, okay, I'm in this state, which action should I take? And this is given by the policy. So the policy is a function named pi, which maps, so a mapping function from state to action. It's like a guideline or an instruction or a handbook. You read, I'm in this state, which action should I take? Okay, according to this book or this policy, I should take this action. If you are familiar with game theory, this is related to strategy. So strategy for game theory and policy for Markov decision process. The return. So let's say today you get a reward of, so this reward today, tomorrow we get this one, and the day after, and so on. So, you want to do the sum of them, because we mentioned that this is what is important, but the reward you get tomorrow is maybe not exactly as important as the one you get today, or especially if if the reward comes in 1 month, this has not the same importance as the one you would get today. That's the reason why you discount it. You discount each of them with a factor gamma that is between 0 and 1, and that you raise to the power of n. So here is 1, here is 2, and so on. So gamma represents the preference you have for the present over the future. If gamma is equal to 0, what does happen? Well, all these terms cancel. You end up only having this reward. Otherwise, with gamma equals 0, to put it another way, if gamma is equal to 0, you only consider the very short horizon. But if gamma is equal to 1, then you consider them all equally. Right? So you have to play with that. So this is called discounted return over an horizon n. And then linking these two concepts, the policy and the return. The policy says you what to do in one state. So we introduce the expectation over this quantity when following pi. So this represents, so this is the expectation when following pi. This expected discount return, what it is? It's actually the sum of the rewards discounted that you should get on average if you listen to pi for each of your decisions. This is what it represents. And your task. Well, now we have one quantity here that is function of a policy. In other words, we can compare pi 1 and pi 2. The quantity associated to pi 1 will be, okay, on average I will get this quantity of discontinued return. The quantity associated to pi 2 is, okay, on average, if I listen to pi 2, I will get this quantity. So you are now able, you have a metric, you have an evaluation metric that you can use to compare pi 1 and pi 2. So it's an operator to make this is greater or smaller than. And this will enable you to make a ranking of different, or a classification, a ranking, an evaluation of the different policies that are possible. And solving the MDP means finding the pi that maximize this quantity. Otherwise, sorry, to put it another way, it's finding pi that is at the top of the ranking if the ranking is based on this criteria. So maximizing the expected discounted sum of rewards over time over an horizon. Again, I mentioned it. If you're not familiar with policy, think of it as a strategy. This comes from game theory. Another, maybe a very little quiz. What is the difference between a reward and a return? They have the same unit in a sense of this is something you collect, but they don't have the same time horizon. Reward is for one step, return is for one episode. That's the difference. Let's take an example to have figures in it. So this is an environment I have designed. Really basic, but useful for education. So we are here at this position, and we want to go there. So think of a car trying to drive along the road. And you have the possibility to accelerate, speed up, or decelerate, slow down, or to maintain your velocity. The velocity is represented with the color, and the higher the velocity, the bigger the jump or the step you are doing in one time step. You have noticed there is here a little point, is to mention, okay, I want you at this part of the road to slow down, to drive slowly. Let's think of, okay, there might be a pedestrian here, so I want to slow down at this process. I want you as well, okay, another constraint or another challenge. I want you to get to this finish line with the velocity of 3. So velocity is between 0 and 4. I want you exactly to have 3. I want you to go as fast as possible to the finish line. So all these requirements can be encoded in this configuration JSON or configuration. So the velocity and the position form together the state. So you described with these two parameters. The action possibilities about the velocity. I want the velocity at the end to be 3 exactly. And the reward, I have designed it manually. You can see if you reach the destination with a bad velocity, i.e. not equal to 3, you get minus 40. This is for the last step, the one with which you cross the finish line. The same applies if you drive too fast close to the pedestrian. But if you get to the end with the good velocity is plus 40. This parameter with minus 3 is useful. For each step you are doing, apart from the end one, you are getting minus 3. It means if you stay at the initial state, you will pile up or you will sum this minus 3, so this is bad. So you want to go and to end as fast as possible the task. Now, let's have a look at the trajectory, a possible trajectory. You start at this position. So 0 means position 0. Velocity is equal to 3. You decide, okay, for some reason, not to change the velocity. So you maintain it. You get minus 3 because this is one step. No other condition applies, so only minus 3. And false is what is called the termination condition. Have you reached the end? The answer is no, so false. Then the next one, this is your next step. from 3, 3 against no change, -3, false, and so on. What it does is quite intuitive. It keeps this velocity, then slow down at some point to get to a low velocity, which is 2, close to the pedestrian, and then speed up as soon as he has passed it. He managed to get to the end with a velocity 3, which brings him for this particular step plus 40. And at this point, the termination is true. He has ended the task. So this is just examples to understand what the definition of Markov decision process actually means. This is an illustration of a policy. We have said this is a mapping from state to action. So one state can be representing in this two-dimensional figure, because we are our two elements, the position from 1 to 19. So remember the straight line, and the velocity. We are here 0, we are 1 up to 4. So this is the initial state. We started always on position 3 at velocity 0. And the color code says you which action you should take. So we read that in this in this state, the policy, which is represented here, is saying you should take no change, i.e. you maintain your velocity. And that is done for each of the states that have been visited. And this is an example of a policy. You can think of another possible policy, which would be the random one. So the random policy will give a random choice among these 5 candidates. This is another policy. Again, just an example to illustrate the concept of policy, mapping states to actions. Well done. Now we have our Markov decision process. This is the formulation of the problem. Now how to solve it. Remember, solving it means finding the optimal policy, the one that maximizes the expected discounted return. Well, remember the big picture here, we will use it. And now we have 3 design choices, or 3 design elements we need to consider. The first one, remember, we have to find the policy. Do we find it directly, or do we use an intermediate step? We will cover that. This is the distinction between value-based methods and policy-based methods. Second choice, or let's say second distinction between exploration and exploitation, especially about starting. And the last one we will cover as well is the relation we have with the environment, and again a distinction between model-based and model-free approaches. Let's go for the first task. Let's start with value-based approaches. Remember the task? I give you a state, you tell me what action should I take. Let's take a very basic example constituted of 4 possible states. This is this grid. The last one here is actually a termination state, which means termination is equal to true when we are here. So we don't need to take any action. The episode is terminated when we are here. For the other 3, the question is which action should I take? And this is illustrated by, or this is given by the policy. So the policy, the optimal one in this case, tells you if you are in state 1, you should go up, and so on. So just an example again to show what a policy is. Remember the task going from here to here. Well, remember as well, we have now a metric that compares the policies which another. And that would be nice. Let's say if we are here, we are on the second state. This would be really nice to have a similar metric function that compares the 4 possible actions. That says us, okay, going up has a value of, I don't know, 1. Going down has a value of 2, and so on. It would be really nice to have a possibility to quantitatively compare the different actions. And this is the concept introduced here. Instead of going directly from here to here, from state to action, we make an intermediate path to what is called Q values. And Q values are represented in this table. So again, we are in this state, and this table collects for each of the action one figure, one number. And this number represents the quality. In more precisely, this number represents the quality of taking this action being in that state. Well, and the new task is to complete or to determine or to fill this table. This is the new task. Once we have done it, once we have this table, we just take the maximum and say, okay, in this state you take this maximum. Mathematically, what do they represent? So again, you remember this term, discounted sum of reward. On average, if you listen to me, if you listen to pi, you should get on average this quantity of discounted return. And for the Q value, this is the same. Not something really important. The Q values is function of two terms, the state and the action. And it represents, again, the quality of taking this action being in that state. How good is it? How good is it? And mathematically, it represents the expectation you have. If you take this action being in that state and then follow the policy pi, how much should you get for a discounted return? If you abstract other actions, i.e., if you take only the best one and you associate it to each of the states, so that would be 10 for the latest, so for the last one, the number will be 9 for the second one and 8 for the first one. You can define as well a metric, a quantity that can rank or make comparison that can evaluate the quality of a state. And this is done with a V of pi. A last thing to conclude with is that V and Q are related to the policy they are representing. So you have a policy, you give me your policy, and then I construct a table, a Q table or a V table, which is the representation of the quality of your policy. So they are linked with one another. This is the value-based approach. Okay, an example or two examples to illustrate the Q functions and the Q tabular representation. You remember our problem with driving on a straight road. This defines different states with the position and with the velocity. And we have just said for each state, so for each column, we need to allocate or to define a value, a Q value for each of the actions. For instance, the value of speeding up being in this state as this Q value, and so on. They are random value for most of them because it was taken at the start, the initialization, but this is the idea, have this representation. You can have for highway driving also similar representation. Think of the state being this image. So we have here 3 states. We have said for each state we need 5 values. So here the values, the possible actions are either you go to the left lane, right lane, speed up, decelerate, or don't do anything, so maintain your velocity and your lane. And then this plot or this histogram graph shows you the relative value of the relative Q values of each actions. And yeah, with the video, since the image or since the state is changing, the Q values are also changing, and what you do is you take the one that has the highest quality, the highest Q value. We will come back to this case, showing that for safety and for robustness is not optimal. The point was here just to show, to illustrate what is the concept of a Q value. Now you might ask, okay, this Q table, I've understood it. How do I fill it? How do I determine these values? Why is it 8? Or I start from scratch, so I have no clue how to fill it. Well, let's think, or let's consider we are here. We are in the second state. The question is, what is the value of this state? I'm speaking of V for the moment, so just abstract over the different possible actions. But what's this the value? Consider as well, let's assume you know the transition reward, which may be here, R. to the next one. So this is your neighbor, and I'm giving you the reward to go to there. And I'm also giving you the value v of this neighbor. So intuitively, what you could say is that since they are close to each other, these neighbors should have similar values. So I will take the value of the neighbor, I will discount it because it's a neighbor, so I have to do one step to get there, and I will add the reward, the things that transition, or the value of transitioning from where I am to this neighbor. And this is the idea of the Bellman equation. Bellman equation says, this is only true for, it holds at least for the optimal policy pi, but the value of one state is equal to the value of a neighboring state, discounted because you have to do one step, plus the reward of the associated transition. This is the idea. This is simplified formulation because you have no stochastic term in it, but really intuitive and really useful. We will use it to solve the MDP. Okay, and let's go back to our environment and use this Bellman equation. Let's say now we are in this state. So we are just about to terminate. We have the possibility to terminate if we go down. You may ask, if I apply the Bellman equation, what should I take for the value of the termination state? And the answer, we take the convention of value is equal to 0 because it's terminated. Well, but what happens then to this part? We only have the value of here is equal to the reward associated to this transition. That's it. We don't have to look for an estimate of a next value. And that's a really powerful property. You can use it to monitor the evolution of your learning phase. I explain why. So here we have, if we have the structure of the reward for the simple road environment, remember that if we get to the final state, the finish line, with the correct velocity, we get plus 40. In other sense, for this particular state, position 16, velocity 3, we are able, if we take the right action, which is the maintaining velocity, to get to 19, which is the terminated state, the finish line. So we are in this case, we are about to finish, and we know that for the optimal policy, the value associated to that should be 40. In other sense, we can monitor the evolution over the training process. So these are the ID of the episode we are training on. And we plot the evolution. And we can, in real time, during training process, have a look. Does it converge to a value first? And does it converge to the expected value? If not, then there is something wrong. So a quite powerful tool to monitor the evolution of learning. Okay, time now for exploration versus exploitation trade-off. It's really, really close to the intuition of human behavior, what we are doing in life. Especially, let's take the example. You have moved to a new city. You know no one, nowhere, no place. You want to go to the hairdresser. So you will pick one randomly. This is exploration. Then it might be not satisfying, so you just move to another one again randomly or with a high stochasticity, and so on. This is exploration. Now consider your situation today. It has been a couple of months. You just continually go to the same hairdresser. No room for randomness. It's about exploitation. And this concept is used for reinforcement learning, and especially when acting with the policy. Let's take an example. You have to fill this table, and then from this table you take your actions. The question is, what or how is it structured? How from this table I can take the action? We have said at the end, if we are really confident in having consistent values here, it's just enough to take the max. So that will be done here. At the end, we take the max, so no room or little room for randomness. But at the start, consider that this table has been initialized with random values. So that might be instead of 8. Okay, this is the best one, but that might be maybe the worst one. So -2, then +2, +1, +10, and so on. Randomly initialized. So you don't want to consider the values first because they have no robustness or no consistency. What you really want to do at start is take a random action among all the possible candidates. So this is done here at the start. How to do that? Well, introducing epsilon parameter, which is a float between 0 and 1. And you say, I consider 1 minus epsilon. And with this probability, I use the best candidate. So the best candidate here will be 8. Here is 9 and here is 10. So I use up and then right and then down. But with the probability of epsilon, I don't do argmax. I actually don't consider the values that are in this table. I just randomly select one of these. Now let's take an example. If I say you that epsilon is equal to 1, that means that this probability is null, so we don't listen to this case. We go for this one. So if epsilon is equal to 1, we act randomly, but purely randomly, only random. On the opposite, if epsilon is equal to 0, then there is no room for randomness. We just take the argmax, so you just apply argmax. We just take the best, the corresponding action to the best, to the highest Q value. Now the question is, we should start from something close to 1 and then go to something close to 0. How do we process? We have to schedule the decrease of this parameter. This is done by having an initial value for epsilon, let's say 0.9999 or even 1, and then we decay it, decaying by multiplying at each episode. We update epsilon by multiplication with a decay parameter, which might be, okay, 0.9999. So it will go a little bit, it will get a little bit decayed and so on until reaching 0, or let's say 0.001. Two comments. The first comment is from experience. This decay parameter is really important, or at least has a lot of impact, has a huge impact in terms of performance. So don't neglect it when you are doing your hyperparameter tuning. Second comment is that this idea of epsilon greedy policy, this idea of how do I go from my Q table to the definition of the policy, this idea is really commonly used. It's everywhere. So most algorithms use it. Really simple, but really powerful. So far we have seen the value-based methods that introduce the Q value in order to go from state to action. There is the possibility to go directly from state to action. This is known as policy-based approaches. I have no time, or I don't have time yet, to cover this topic, but just mentioning 3 strengths it has. First one, there is kind of simplicity because you don't need to store these Q values. The second one is it enables you to define stochastic policies. Stochastic policies means this was not a stochastic policy, because with value-based, for each state, you have to map to one action. There is no other choice. You can't say, if you are in this state, then I would recommend you to randomly decide between go up and go left. This is not possible. You have to be strict and say there is only one option, go left. But for some particular problems, this is good to have this stochasticity. Think of this game. In game theory, it can be shown that the best or the optimal strategy consists in choosing randomly between the 3 of them. This is not possible with value-based. This is possible with policy-based. It says you 1/3, 1/3, 1/3. And the last big advantage is that you can cover more easily continuous action space. Remember, we had this case of for instance, driving on the highway, should I go left, go right, slow down, and speed up, and so on. And for each of them, we have a Q value. Then we were selecting the best one, the highest one. This was the argmax operation. This is feasible for discrete state space, but it becomes quite tricky to do with continuous space. You can think, for instance, this might be the level of acceleration, or let's say the steering angle you have to make. And to find the optimal point, you have to put some implement some optimization, which is not trivial, or at least which is computationally demanding, which is not the case with the policy-based approach, because you don't have Q values. A quick word, very quickly, about how do you learn in policy-based approaches. So again, this is your state. An example here is you defined a picture with pixels. The pixels are processed, and at the output, you have for each action, it recommends you to take left with probability 1/3. Up is the most likely one. You should have it half of the time. So this is one policy when doing policy-based approach. One result. Now let's say we have experienced one episode, so from here to the end. Then we say this is a quite good experience because the return was +1. So what we want to do is, for each individual decision that has been made, we want this decision to be even more likely next time. So to increase the probability of repeating this decision. And then you will find some parallel with supervised learning, and you can apply these powerful tools that are available already for supervised learning. This is a very rough intuition how to learn when doing policy-based approaches. So we have spoken about the policy, about the epsilon greedy for exploration against exploitation. Now, time to mention the relation we have and we keep having with the world, the environment. So there is something important to note. We are playing with it. For the moment, each of our experience enables us to improve our policy, to improve our behavior. This is what we are doing. We are experiencing in order to improve this value and policies. Another thing to note is that the transition function, how you are taken from S and A to S prime, this function is only known by the environment. And the same applies for the reward. In other words, if I say you are in S2, let's say you are at 20 kilometers, you want to speed up. What's the probability of getting to 30 kilometers? Actually, you don't know. You have no idea of this transition function. And in the same vein, what's the probability of getting +1? You have no idea. This is only from the knowledge of the environment. Nevertheless, once you are doing, or when you are doing this step, you are collecting information about S, A, S prime, and R. So this is one tuple, one experience, we have already said. You are using it to update your model, your Q values, for instance, to improve your policy. And the idea is, why not using this tuple to try to model these two functions? Why not observing, okay, I was at 20, I asked to ask, I'm now at 30. So I might have the feeling when I ask to speed up, then I should my velocity should increase, and so on. This is the idea behind model-based. What you want to do is to have two tasks when experiencing one step. The first one is to gain in quality with respect to the return, and to gain with knowledge how the model evolves. At the end of the day, what you want to do, this is quite extreme, but is to disrupt, to remove the need for an environment and substitute with a model of this environment. So when developing your solution, you can ask yourself, After learning, can the agent make a prediction about the next state and the next reward or the reward before it takes each action? If yes, then it is the case of model-based. If no, it is called model-free. All right, let's say now we have done model-based. We are no need now to get interaction with the environment, since we can predict. I can predict that if I am at 30 and I want to speed up, I will be at 40 next time. If we are in this case, then we don't need the environment, and the problems comes in solving the MDP, finding the optimal policy. What you can use is what is called dynamic programming. There are policy iteration or value iteration. The idea, really quickly, you start with a random policy. You want at the end to have the optimal one, but you start with the random policy. Then you evaluate it, assess the quality, and then improve it. And then you do that, you iterate until you converge, you're converging. And this is important. You have no interaction with the environment since you have a model of it. This is the idea, model-based versus model-free. Okay, back to results. Here are some results. One is for model-based, the other one is for model-free. So having a first look, what differs, you notice they both represent the policy you have to implement. Here, however, you don't have any decision, or the policy says, I don't know. So this is model free, because with model free, you didn't have the opportunity to explore it. You just rely, all what you are saying, all the policy domain is based on what you could experience. And in this case, since we are always starting with velocity 3 at position 0, we never had the opportunity to explore this region. So we can't say this was good or this was bad, or in this case, you should take this one, or at least not with a tabular representation. With function approximation is possible, but not with tabular representation. That's model free. On the other hand, here we have also a representation of the policy, the position, the velocity here. So for each position, it is one state, and for each position you have one color. Then refer to the color code here to know which action you should take. So again, these two figures represent a policy, describes the policy. The difference is that this one was made with policy iteration, the other one with value iteration. Just to illustrate the concept of model-based versus model-free. Model-based, you have the full knowledge, so you know if you are speeding up when being in position 0, you will do that. So you can fill the part at the bottom of the plot. Okay, just to sum up, reinforcement learning can be divided, we have seen, in model-based versus model-free approaches. What is control versus prediction? Control is exactly what we have been busy with, i.e. trying to find which action should be taken in one state. On the other hand, prediction is about trying for each state to find what is the value of this state. This is another question. Determining the action you have to take, the optimal action, or trying to assess, evaluate how good is this state. We have quickly mentioned the dynamic programming for model-based. I've been implementing this policy iteration, value iteration, and presented some of the results. Now time to consider the control for model-free, i.e. from the Bellman equation, how do we use it to update our Q table, for instance? We will be using the very popular SARSA method and Q-learning, and mentioning the Monte Carlo as well. So about SARSA, what SARSA means, or where does it come from? You might have identified S is for the first state you are in, A is the action you are taking, and R is the reward. This leads to another state, which can be S prime, for instance. And being in S prime, you can, I don't know, take action A1 based on the same policy. But at least the first one has been experienced. Now the question is, you know, for value-based, you have to update your Q table. How do you update it? This is not so obvious. In particular, you have been reading in your table this value because you were said, okay, you are in state S. So for action A, you read this value. Now the question is, how do I update it? Should I make it bigger or smaller? What would be really nice would be to have the ground truth, i.e. the correct value, or the value of SA for SA, but this time with pi prime, the optimal policy. But this is of course not available, otherwise we will already know the optimal policy. So you have to fix one target or one value you aim at, and then compare your current estimate to that target. But how do you get a target? One solution would be to use this optimal equation, where Berman equation says for the at least in the optimal case, when the policy is optimal, then this relation holds. So what you want to do is use your S prime you have been observing. Take an action, another one, A prime. So this is for the neighbor state, the new state. And compute for the initial one, for the initial state action pair, a Q value. This Q value will be your target. So you have now a Q target on the right, and you can compare now your Q estimate to this Q target. And then this is exactly similar to what supervised learning is, where you have a label or a ground truth. You have an estimate. This is the current estimate your model is giving you. You compute the error, the difference between the two. You apply a learning rate to update your Q estimate, and so on and so on. So for each experience, S, A, R, S, S prime, you apply it and you update the corresponding cell in your table, in your Q table. This is the idea of SARSA. So SARSA is represented here. The question in this slide is, how do I update the Q value associated to this state? This represents a state. This represents also a state, the next one. And the little black points represent the action that has been taken to transition from one to another. And what SARSA says, so SARSA belongs to the family of temporal difference. SARSA is saying you just take this step in order to update this value. On the other hand, the Monte Carlo method says you want to update this value, or at least the value associated to this action state pair. What you need to do, or what you should do, is wait for the termination of the episode. In Go, for instance, if you have lost or win, and then roll back all the information up to this point and accordingly update this. So the advantage of that is it is unbiased, because here it's biased. You are building your Q targets based on estimation, but this is not ground truth. Here you're really waiting for the end. You will get a reward at the end. You can compute the return and so on. So this is not biased. But this suffers from high variance, which is not the case for the methods. So there are some trade-offs to have. What you could do if you have the transition model or model-based is, again, in order to assess this value, you can imagine or predict, since you have a model, what happens if I go there, then I will go there, and so on. But again, only doing one step here from Israel. On the other hand, this is, let's say, brute force, or if you have all the information, or if you can afford it from a computational point of view, you could explore everything and expand each branch until the termination state. So this is the termination state, and then roll back the information. Again, the goal of this slide was to know how do I update the value corresponding to this state. So this is a very short overview of what is possible for updating the value of one state. Okay, let's see maybe in particular how SARSA works, and just consider this line, this one, where we are updating our estimate of the Q value. So we have been experiencing one step. We saw that we went from S and A. We observed R t plus 1 and S plus 1, ST plus 1. Now the question is, how do I update my estimate about QSA? Well, what we have seen is you compute the error. This is the red term. And then in the error, you have the difference between the target and the estimate. So the estimate is here, and the target is the first term. And inside the target, we have the reward that we have just seen, and the discounted Q value associated to the next state action pair. The question that I ask you now is what value can I use for this QS prime A prime? This is the question. So let's consider our case where we have our tabular representation of the Q value. I'm saying you, for instance, all right, the S prime is this one. So you know this is S prime. This is your current T table. It might be the optimal one, but probably not. So you have 4 values because 4 actions. Now the question is, which one do you use? One possibility would be take the average of all the 4 values. This will not be SARSA, this will be expected SARSA. This is one possibility. What you can do is take the max, in this case plus 9. This is not called SARSA, this is called SARSA max. And SARSA max is also called Q learning. Quite popular name, Q learning. But in both cases, you are not implementing your policy. And the third possibility you have is, well, I am given a state, which is S prime. I have to take one action. I just use my policy, and I apply it to S prime. In this case, since it's epsilon greedy, there are some chance that I take a random choice. Let's say it happens. So I will, okay, I'm giving this action to be taken. So the Q value associated to this, I read it in my table, it's plus 8. And I use it to build my TD target, sorry. My TD target. Just to sum up, these methods of SARSA, the different one, which belong to temporal difference methods, are really similar. They just differ at this point where we want to estimate the target. In order to compute the error, we saw that SARSA actually reduce the policy, the current epsilon greedy policy. This is called on-policy learning, because you are reusing it to estimate your target. What you can do otherwise is don't use the policy to make your choice, either take the max or take the average. And in this case, it's not on policy, it's called off policy. You're not using the policy in order to estimate the Q target. This is the difference. All right, and when you apply it, when you iterate, when for each episode, so this is here the episode, you collect the rewards, it gives you the return, and then you plot the return. This gives you the blue line. And then you can smooth it by taking the average over 100 episodes, and it shows you the yellow line. And the algorithm updates the table so that it becomes even better with respect to this goal of maximizing the expected return. And at the end, we converge this to the maximum, to the optimal policy. Just an example to show the learning process. So far, we have been using a table in order to store and update our Q values. But in particular problems, it can't be the case because it's too computationally demanding. Let's take an example. Here we have a problem where the state is composed of many pixels. And again, we have different actions that can be taken and applied to the joystick. And we want to estimate the values of each of these actions. So what we did so far is using a Q table, and for each state, we have the different Q values. But this is not tractable, or this is not feasible when the state is too big, because the table will get too big. The solution for that is to have a function approximator. So the function approximator will be given the state and will output, okay, how many actions do we have? So for each action, we output one number, which is the Q value. This is done, for instance, in deep Q network, where you are using a neural network as a function approximator. The idea is the following. Here you put your state, So we have only 3 elements, but you will need one for each pixel at least, plus the RGB channels. And here is the output. We have only 2, but these are for the actions. We need 1 per action, and then this value will be the Q value corresponding to the first action, and so on. So the advantages, there are 2 main advantages. The first one is that now you can cope with really, really big states, which was not the case with the tabular representation. And the second one is that, obviously, with a function approximator, you don't need to have seen the state in order to have a Q value associated to that. This was not the case here because we haven't met, or because we haven't seen these states. We couldn't get, or we couldn't estimate the value of them. This generalization property makes the value, the function estimator, really powerful. And this is done, as mentioned, in deep Q learning, with the Q mentioning the deep Q network, with the Q mentioning the Q learning, so SASA max, we have just seen. So using a function approximator instead of a Q table is a good idea, we have seen. Nevertheless, for stability, we need to include additional improvements. So I will mention 5 of them, and then I will cover only the first one. The first one is about decoupling the time when you explore and the time when you actually learn and update your model. It's called with an experience replay. We'll see that in a minute. The second idea is about fixed Q targets. So you remember, we need 2 things to compute an error. The first one is the Q estimate, and the second one is the Q target. And both are read from the same model, from the same Q table. And for stability, it is not good because you are updating something, you are updating your model, but at the same time, based on your model. So this has to be decoupled for stability. This is the idea of fixed Q targets. Dueling, it says, well, you remember our table, we had some numbers in it. But do you remember the numbers? No, it's not important. What you remember is which of the 4 actions has the best or has the highest Q value. In other words, you are not interested in the absolute value. It's only about the relative. Which one is the best compared to the one? No matter if it's 20 or 10, what is important is that it's bigger than the other one. So you decompose your Q value in one common term shared by all the actions, and then the difference is made by what is called the advantage term. That's the idea, splitting it to make it more stable. Then comes double DQN, again, Q learning, SASA max. You take the max of all the possible Q values for the next state. Taking the max is actually overestimating. So that's addressed by double DQN. And the last one, actor critic. You remember I distinguish value-based, policy-based. The idea is here to combine both of them. So you have a critic, which is value-based. You can think as a supervisor or the parent, and you have an actor, which is a student or the baby, which is acting. And then the assessment is done by the critic, and the actions is done by the actor. Again, same idea, decouple things to make things more stable. Experience replay. Remember, we are seeing these tuples for each step. And the question is, what do we do with that? We saw how to update our model with this. So maybe the other question is, how often do we update it? Well, it has been seen that it's better to decouple, not to take immediately what we have seen and apply it to the model. Just wait a little bit and split between 2 activities. The first one is practice. So you play, you try, you experience, you collect your tuples of experience. And the second step, when back home, or I don't know, but the second step afterward is you use this pool of experiences, and accordingly you update your model. And then you start again. You practice, collect experiences, and then in a second time you sample from it and you learn. What does sample mean? You have stored several tuples in a big memory place, and now comes the time of sampling. So you are randomly, for instance, getting samples from it, which is called the replay buffer, and then you use it to update your model. This is the idea of experience replay. If you want a more advanced version, there is this prioritized experience replay. What it says is, some experiences are more important than others. You remember when learning to ride a bicycle. You probably remember all of your fall or accidents where you did something wrong. And that shows that when acting, when learning something as a human, you put different importance on some experience than the other. This is called prioritized. There is a metric you have to introduce to say this tuple was more important in my process, so it should be considered more often or more seriously. Prioritized experience replay. So we have covered the major concepts, very basic ones, but major ones, about reinforcement learning. I want now to take a couple of minutes speaking about the perspectives for RL, especially applied to autonomous driving. So to compare autonomous driving reinforcement learning approaches with, let's introduce the rule-based methods, a competitor to RL, which says, for instance, this is a if-else statement. If the gap with another vehicle is smaller than 10 meters, then slow down, otherwise maintain. Really basic, really simplification, but now we have something to compare with. And using this comparison, we will set a couple of advantages. First one is about RL can do generalization really well. Remember what I said with the function approximator, when you can estimate a state without having explored it. This is the same thing here. Although you haven't seen a scenario, or although you haven't experienced or be confronted to a particular situation, you still can make a decision. So that's the one strength of reinforcement learning. In the same vein, you can address complex reasoning without having to design manually with an expert knowledge definition of all the rules. You can cope with you can have the benefit of learning over time. So you're improving your model over time. The more data you have, the more data you are exposed to, the more experience you live, the better your model gets. And last but not least, you can, if you modify a little bit the formulation, for instance, having this partially observable Markov decision process, you can really well cope with uncertainty, which is a very important benefit when addressing autonomous driving situations. On the other hand, there are limitations, and especially when confronted to rule-based methods, this is difficult to make sure that traffic rules are respected. But 100% sure, not 99.999%. It's about 100% sure. This is not obvious. The same applies for safety constraint. This is the strength, of course, of rule-based. This is categorical. Another thing, not necessarily, but it can be more expensive from a computational point of view to use reinforcement learning approaches. You have to decide if you use online, offline. This is a design choice. You might have already guessed it, but the word of driving is not MDP. There are some tricks, stacking frames, for instance, or having a recurrent network to cope with the idea that the future is not only dependent on the present, it's also depending on the past. So you have to adapt the formulation. Some drawback, or at least one strength of the rule-based method, is that is really interpretable. You just have to go to the different statements and see in which case you are. Makes it easy to debug. And RL as a machine learning tool requires some hyperparameter tuning, model tuning, which is not required for that. So strengths, limitations. What I want to say with that is that both make sense, and the best idea would be not to have it alone, but to make a fusion of them. And merging the two approaches makes sense, especially for safety. So for safety, what you can do is called action masking. Remember this scenario where we are driving on the highway, and for us it's obvious in this particular scenario there is no point taking the action go to the right. It will just take us off the road. So why not saying in this particular case, I forbid you, no need to explore, no need to contemplate, you only have 4 actions. And this could be done for safety purpose, where we know here is the same case. There is no point going to the right. It shouldn't be too much effort to code that. It shouldn't cover all the possible situations, but just strict rules where you can then make sure reinforcement learning won't even consider this option. There are different benefits of that. The first one is that it reduces exploration. You don't spend time having a look, okay, what does happen when I'm doing that? Maybe more importantly, it's about safety. It just increases safety, robustness, and interpretability. So action masking, an example of merging rule-based and reinforcement learning for autonomous driving. Let's mention a couple of research directions that are currently taken for autonomous driving. You remember my configuration here of the reward structure. In particular, the cost for each step was set to -3. You could ask why not -2, why not -4? You will be right. The idea of inverse RL is, okay, this step of designing it is quite a hard task. What if instead we try to learn this? Learn means in this case we observe a good driver and we assume that his behavior is actually related to a reward function that is hidden. This is the hidden state. And we want to get access to have an estimate of this latent variable. This is the idea of inverse reinforcement learning. Learn the reward function. There is what is called hierarchical reinforcement learning. The idea is again to decouple, to make it simpler by decoupling. You decouple the low-level decision, for instance, all what is related to speed control, go a little bit faster, go a bit slower, and so on, from the high-level abstraction of decision, i.e., overtaking someone. This is a higher semantic decision. Multi-agent, we have already mentioned it, but if you have the opportunity to communicate with other cars, with other participants, with the infrastructure, then you could together plan a better strategy. For instance, if you are crossing and then you know that he will be going straight, then you will stop. But if he is saying, okay, I'm turning, then he will be free. This is just an example. It requires vehicle-to-vehicle communication. But assuming you have it, this is a good opportunity to apply reinforcement learning. The POMDP means partially observable Markov Decision Process. This is actually the case for every driving situation. The sensors gives you only approximated values about the state of the other participants. For instance, the position, you are not sure if it's exactly here or here. As a result, it's difficult to make decisions if you are not sure. And this is just about the uncertainty in measurement. This is not mentioning the fact that there are some occlusion. With occlusion, you have no idea if someone is coming. And with all this uncertainty, it's really difficult to make prediction. It's really difficult to make decisions. So what you do is you formulate it as a partial observable MDP, where you try to track, to update beliefs about the state. You can't access to them, but you try to track them and make decisions based on that. Intrinsic motivation, the idea is, like for human, I was saying so far the reward you get is from the environment. But actually for our real life, we are also able intrinsically to self-assess our decisions, to say that was good, that was not good. So that's a distinction from the reward given by the environment, extrinsic. Yeah. And last one was about multi-goal learning. You still keep your 5 actions, for instance. You still keep one set of action. You have still one state, but what you do is you are defining several goals, and you will get as a result several Q tables. For instance, one goal would be, okay, I have to drive and learn to cross an intersection properly. The other one would be the policy that says you how to avoid going too fast close to pedestrians. Now you have 2 policies. They both take the same state. They both propose you an action. Then of course it's the question, how do you select if they are not agree on what doing? This is of course the question of multi-goal learning, but the idea is again, decompose, decouple, make sub-problems from this problem to make it simpler. So that's the research direction to keep in mind. This brings us to the conclusion. So what we have seen today is the different concepts of reinforcement learning. In particular, the intuition that is closed, we can draw parallel with the human behavior. Not to forget the distinction, the several distinctions we saw. In particular, remember that the MDP is used to formulate the problem, that reinforcement learning is about solving it, trying to find the optimal policy. And if you heard about deep learning in the context of RL, it's really about having a function approximator instead of a tabular representation. Maybe the challenge is to mention the state representation. We have seen that if the state is big, this is not so easy to address. Also the delay rewards. We have mentioned it for Go, where it's quite far away the point where you get a single reward, so that's a problem. Exploration strategies, it's not so obvious how to organize it so that you see everything, but at the time not spend too much time on it. Fine-tuning, it's a machine learning approach, so hyperparameters, in particular I mentioned the epsilon decay has to be tuned. Last but not least, especially in context of autonomous driving, the robustness and the verificability is not so obvious in the genuine or vanilla version. If you want to go further, I encourage you to try to implement your algorithm or go for additional tutorials. There are really good materials available on the web, especially these 3 tutorials from the US and from the UK are really brilliant. I encourage you to have a look at the OpenAI GIM environment to understand how they are built. So the MDP is already defined, so that you just you have time to concentrate on testing different RL algorithms. If you prefer textbook, then go for Sutton and Bartow. This is definitely the Bible for RL. Again, thank you. I hope you enjoy it. Obviously, YouTube will be proposing you new videos to continue with. Some will be familiar to you, some not. So it's really about exploration against exploitation. So if you could just make a thought and think, well, I'm about to make a decision. So can I model it as a MDP? In this case, what should be my policy? What can I expect for a reward? And what's about my horizon I have to take? If you make this thought and these questions, then for sure you will have learned something today, and I will be really happy with that. I will get an intrinsic, at least, quite high return. Thank you again. I guess we have reached the end of the episode. Thank you.